So advanced compactor logic, express compactor. So when you have express compactor, controller masking logic, we'll have a additional controller. Okay. Majority of the times this is default, which we use in real time. Okay. So you have AND gates for masking. You have XOR gates as usual. So the AND gate other input is from a mux, and the input of this mux will be XOR decoder and a one hot decoder. Okay. This controller is provided to provide the best value here in order to avoid any loss of data. So for example, in the process of XOR or masking, you should not lose the original response value, right? Tool has generated pattern and it captured some value. The captured value should be as it is driven out, right? It should not get modified in the way. So for that, okay, we have a proper XOR decoders, one hot decoders, okay, that will avoid any data loss. Okay, so these are all scripts only. Yeah. So understanding scan chain masking in the compactor. Okay. So one common problem with different compactor strategies is handling of excess unknown values. Scan cells can capture X values from unmodeled blocks, memories, non-scan cells. So there are many reasons. Unmodeled blocks means while during during pattern generation, you might have not read proper libraries of certain modules, which became black box modules. So for them, it is like a unmodeled. Unmodeled blocks means for which you did not read the libraries fully. And memories, obviously, memories will be hard IPs. So memories you cannot read. So memories output will be X propagation value. You will have X. But there are strategies now to bypass or to mask the X propagation of memories. Now the tools are so smart now. And non-scan cells. And we specifically make certain part of design, okay, to be non-scan. That means certain OCC memories, any additional clock generator circuits or visas or any other cells that no need to, we don't want to make them part of DFT logic, and we don't want to convert them into scannable flops. So we make them as non-scan by default. Okay, so such non-scan cells, anything that you make in the process of scan insertion itself, they are already non-scan cells. So if you are getting a value out of non-scan cell, that also might come as a expropagation because that is not part of scan, and it is a functional logic. Make it as a functional. Non-scan means obviously it is a functional logic, and functional logic output will be X when it is not part of scan chain. That means the sequential cell part of functional logic but not part of scan might give out X propagations. Okay, so NX captured in chain 1 will then block the corresponding cell in chain 2. Okay, so chain 1, chain 2, and this is the output value that you capture and make it to the output. Okay, so 1 and 1 will become what? XOR 0. 0 and 1, what will become? 1. X and 0, XOR behavior, X. 1 and 0, 1. X and X, X. 0 and 1, 1. 0 and X, X. 0 and X, X. 1 and 1, 0. This is the output that you get, right? So the tool records X in the pattern file in every position made unmeasurable as a result of the actual occurrence of an X in the corresponding cell of a different scan chain in the same compactor group. So this is referred to as X blocking. Okay, how to anyway, let's continue. The capture data for chain 1 and chain 2 that you would see in the ASCII pattern file for this example would look similar to like this. Okay, so the excess substituted by the tool for actual values, the unmeasurable because of the compactor are shown in red. Okay, so how do you resolve X? Scan chain masking. One is hot masking and other non-masking logic. So let's take one hot masking. Only one chain is observed via each scan channel compaction network. That means at a time, only one chain output will be captured. You don't bother about other chain. Okay. So even if there are excess in one chain, okay, one hot masking is sufficient enough to detect all the faults. Tool will be able to identify that particular fault to a known value. Okay. So in real time, one hot masking helps in for a tester debug. We we purposefully generate one hot patterns before delivering to the tester, so that you have each individual compressed chain pattern. Okay, so that will become a gold pattern. Tomorrow it is very difficult to debug the compressed chain failures. Okay, because the EDT itself is a magical structure where the patterns are, you don't know how the structure forms. Okay, because this is the concept or methodology introduced into the tool. So tool's behavior, this EDT gets upgraded day to day, and tool, we cannot 100% understand the tool behavior. And two channels we have made into each channel holding 100 chains. Now we have total 200 subchains. If you want to trace a circuit with 200 subchains and in which chain the failure is there on tester, it is very difficult. In our environment, we can do some simulation debug and all, but in real time we cannot. So there is a express compactor the other way, which will how do I say, at a time all multiple chains will be observed, 1, 2 or 3. Okay, now tool will add that and get other input is there, no, so it will program accordingly and it will create that output value, but not in this way, in this way. So the chain masking value might change depending on the pattern. Okay, so I mean, each chain we have one AND gate, right? So this two AND gates output will be going into compactor. So this will be programmed in such a way that you get the original value that you want to capture.
Sir, your screen is stuck, sir.
Screen is stuck.
Yes, sir.
Let me reshare, okay? Is it visible now? I'm showing the
Yes, sir.
example of scan chain masking. The cursor is moving, right? You're able to see? Okay. Okay. When using scan chain masking, the tool records the actual measured value for each cell in the unmasked selected scan chain in a compactor group. So the tool masks the rest of the scan chains in the group, which means the tool changes the values to all X's. With masking, the captured data for chain 1 and chain 2 that you would see in the ASCII pattern file would look similar to this one. So this is masked, this is unmasked. So what the tool is trying to do is it is trying to observe only chain 2 once at a time. At a time, only one chain is observed. Okay, the rest of the chain is entirely masked to a unknown value. Okay. So it will be something like this in pattern. Chain 1, chain 2, chain 3. The fifth pattern, an EDT channel output. These are the input values. Okay, there is one more concept called fault aliasing. Okay. So fault aliasing is also another concept. So assume one fault is observed by two scan cells and that these scan cells are located in two scan chains that are compacted to the same channel. So these two chains are capturing the same value. So as I said before, two channels output is captured by XOR gate. Okay, and one channel input is 1 and the other channel is output is 0. Okay, you are getting XOR value of 1. Okay, when you have 1 and 1 or 0 and 0, then your output is 0 and 0. Correct? So this is what we call tool. I mean, tool is not going to absorb the correct value because of the behavior of XOR. You are losing some data. Okay, so you will not be able to capture the correct fault. Okay, so because of this aliasing effect, fault aliasing effect, we are also using scan chain masking. Same. So for fault aliasing is one scenario where we'll come to a scenario where because of our behavior, both the chain pattern value is lost when you have 1 1 and 0 0 values. Okay, so for that we have a solution of again masking, only the same masking. Okay, so when you have 1 1, you'll have 1 here and have 1 here also as well, right? So 1 0, you'll have 0, and when you have 0 1 and 0, XOR output will become 1. So you have captured the fault value from one chain successfully. So in second attempt, see when first attempts in masking, always remember when you have two chains going into XOR gate, or more than multiple chains, at a time one chain only will be observed. One chain output is only observed properly without any loss of data, even if requires masking. Okay. After that, second chain output will be observed. Express compactor will try to make one chain stable entirely while one chain is getting observed. Okay. Is it clear?
Yes, sir.
So this EDT abort faults we will discuss in ATPG. Okay. Now it's so not required. Okay. We'll discuss EDT abort in ATPG. Next, I'm going to discuss on this is dual compression configuration. I don't want to confuse you with this for now, so we will not discuss that. So additional power controller is just to this is enabled for a low power consumption. Okay, so this power controller is introduced into EDT structure to analyze the power fluctuations of each and every pattern. Okay, so the values collected are before giving it to decompressor and after the decompressor output, both are captured. So it's a low power shift enable. So when you have low power shift enabled, so tool will try to tool will try to analyze the power during shift peak power. This will be helpful in the later for our analysis, and we'll try to adjust the power. The physical design team will add or modify the power ratings and all with respect to pattern behavior. Okay, this again we can discuss again once you understand the concepts better. Okay, because in the very beginning, so you might not digest the concept now. Okay, we'll go understand this slowly. Okay, so there is a chapter here also, low power shifting. You can understand from this. Next, design rule checks. Okay, in compression, first thing is you will get either trace violation. You will stuck with the trace violation. Okay, before going into the compression chain itself. You will not be able to trace the compressor chains, because either the clocks are not defined correctly, constraints are not provided correctly. Okay, missing collaterals or any kind of things can produce issue to the chain tracing of compressor chains. So I'm talking this EDT is after scan insertion, right? Okay, during compression. Okay, let me make it a little bit clear for you guys, not confused. So after scan insertion is completed, okay, you write out the scan def file comma SPF and what we call SPF will automatically have this, right? And still file. I mean, SPF and still file are both are in still procedure file, or a scan procedure file, or a protocol file. One more. I mean, scan inserted netlist, obviously. CPL, BDC. Okay. So all these files will be writing out. So during compression, let me, yeah. Sure. So this is how you you read the DDC file. Okay. And you set the design block name, you link. After linking, you write the configuration for compression. Okay. And you provide the clocks information again. And data port information, data in data one, all this information, and configuration, how many chains. Okay. And compression configuration of chain count, how many internal subchains. Okay. So you have how many partitions you have. If you have only one partition, only one codec. Okay. No need of multiple codecs. You will do create test protocol, report DFT partition, preview DFT, insert DFT, DFT DRC. Okay. And you will write out scanf, DDC, and protocol. In this process, when you try to add all this information and create test protocol and come up to this level, you will face some trace violation. Normally, what happens is when you are doing scan, you are using a scan compression technique. Synopsis compression technique like codec. You will not see T1 violation, T1, T2, T3, T4, T5 trace violation. Those violations are in from Tessent. Tessent naming convention is T violation, trace violation. In Synopsis, you will not see those violations. You will directly, after DFT DRC, you will come across seeing if there are any chain blockages because of improper clocking information, control signals are not provided properly, any gating information that will end up DRCs. Okay. I did not see any DRCs explained in this synaptic document. But let us understand in Tessent. Okay. In Tessent, it is very evident you have DRC violations checked. This is one biggest advantage also for many of the vendors going for Tessent compression technique. Okay. So what we will check in Tessent compression. Okay. First we'll check is EDT control signals, EDT clock, EDT update, EDT bypass, EDT reset. Okay. All these signals are clocking correctly. Okay. Do they have correct value during the test protocol? And input channel pins to the decompressor and from the decompressor to the scan chains during shift. That is K19. Let me show the image. Okay. So this is the front part, right? From where primary inputs to the primary inputs are channels. Okay. To the scan chains. This is the internal scan chains. This is decompressor part with bypass enabled. Okay. So starting from primary input to the scan chain output, scan first cell output. Okay. At every stage, tool will verify whether you are able to trace back. I mean, able to go through. Okay. So the value is going through properly without any issue either at any stage, at any of the stages. Okay. And there is no expropagation till this part. Then DRC is clean. That means tool is trying to uh, create a pattern and load right during shift in. During shift in, it has created 1011. So that 1011 has to reach to this first one value has to reach to here. So likewise for every input reaching up to the first scan cell, because any value that comes and that's had to be shifted in has to go through this first register, right? So first cycle 1 will come, in next cycle 0 will come, this 1 will move to here. These are shift registers, right? So every clock pulse the value gets shifted to the next cell. Likewise, how many flops you have, that much pattern will be loaded or shifted in. So till this point, tool will check whether you are able to load value to these cells, scan cells. Okay. So if you have any issues at any point of time, you'll have this K19 violations. So you have to debug this. So K19 are very rare to see unless your flow is messed up or physical design team has made scan chain reordering. You're working on a post silicon debug post placement and routing netlist. Okay, given by the SD team. They have added some additional logic or additional cells or changed the existing scan chain order. Okay, so scan chain order can be changed only by the physical design team for a purpose of placement. Okay, so once you do DFT and give to the physical design team in 1.0 version or the final freezed version, so once your netlist is freezed, that means there is no design changes. So the last netlist that you release to physical design team, they will also freeze there. So they will freeze it and they will do timing, final timing and routing everything, and they will give you final netlist to perform pattern generation and simulation only validation. So at that time you might see this K19 or K22 violations because of change in scan chain order.